Hi, everyone. This is Jason Key at SBGrid. Currently at my house, working from home, but close to SBGrid at Harvard Medical School. And thanks for joining us today. I'd like to welcome Tom. Thank you for kicking it off for our center. So Tom is in Los Alamos at Los Alamos National Lab and is a contributor to the Phenix project from the beginning, and it was resolved before that. And today he's going to talk about density modification for cryo-EM maps.
Thanks very much, Jason. And thanks to Piotr and Michelle, Pete, Jason, and the whole SBGrid for doing this. I think it's a really great idea. And this is a chance for all of us to say hi, talk to each other, help each other out a little bit in some difficult times. So thanks. I think it's really great. So today we're going to talk about density modification and model building with cryo-EM maps. And those of you who are crystallographers will recognize some of this, but you'll see some of it's not the same. And those of you who are cryo-EM people will see that there's some elements of things you've been doing and some things that are different. And so let's go right into it. So here are the things we're going to be doing. We're going to start with two half maps. So two maps that were created with each half of the data in a cryo-EM data set. This cryo-EM data set is going to be human apoferritin. The data set goes to about 1.8 angstrom, so it's a high resolution data set. You can see these two half maps, if you're glancing at them as I'm talking, they look pretty nice. And both of them are very good individually. They're not exactly identical because they're actually different data. And what we're going to do with these is we're first going to combine information from those two half data sets and expectations about what a map ought to look like. And that's going to improve the map overall, and we're going to create one density modified map out of that. And that's the one in yellow that you can see. And if you look carefully, you'll already see there's some differences between the half maps and the full map. And I'll show you a little bit more detail about that later as well. Once we have a density modified map, we're going to do automatic model building to create a model that matches that map. And you're going to see that the first run through of automatic model building will work pretty well, but it won't be perfect. There will be a couple mistraced places. And we're going to fix those also automatically by deleting the bad parts and rebuilding the parts that were bad, and doing that using a tool, assign sequence and sequence from map. Okay, so let's go through this. And the first thing is going to be, how does density modification work for cryo-EM? So let's talk about that for a couple minutes now. So density modification is a procedure that basically makes use of expectations about one part of a map and uses those to improve another part of the map. This transfer of information from one part of the map to the other is the crucial element of density modification. It makes it different from other tools like real space tools such as histogram matching, which only operate locally. And I'm going to show you why this works and why it can apply to cryo-EM maps. So the map on the left is the average of those half maps that I showed you in the previous slide. You can notice that this doesn't look completely like a perfect map. One thing is the solvent region isn't flat. It has noise. And that's fine. That's part of the reconstruction process, and that's expected. But we know something about that region. We know that the density is more flat than what we see in this picture. We also know something else, which is related to the histograms I mentioned before. The distribution of density values in the protein or macromolecule region, we would expect those to match the distribution of a typical protein. In this particular one, they don't match it yet. Once we density modify, then we'll obtain histograms that are more similar to the original, to the true ones. Now, this is the original map. This is kind of the best version of the original map that one could produce, at least that I could produce, and then the best density modified map on the right. If you notice, look carefully, the original map is pretty good. But look at that tyrosine. It doesn't have perfect shape. That hydroxyl looks a little funny. In the density modified map, it looks very similar, but the details are better. And this is going to be the consistent thing about density modification and cryo-EM, is that the low resolution data in general is already very, very good. And you're going to improve only the highest resolution part of it. That's not true in some cases. Some cryo-EM maps have relatively poor information throughout the resolution, and those can be improved more with density modification than others. So let's see exactly how this is done, and how can we possibly transfer information from one part of the map to the other. So maps are calculated in cryo-EM, as in crystallography, from Fourier terms. So I've shown some mock Fourier terms and a map that consists of one little peak. The key idea here is that if we change one Fourier term, that affects all the points in the map. So here I changed one Fourier term, actually I took one out, and notice there's ripples throughout the map. What that means is that an error in one Fourier term leads to correlated errors throughout the map. Why are they correlated? They're correlated because they're all coming from the same thing. That means the errors here have something to do with the errors there. So what density modification does is it makes use of that information. So fixing a Fourier term based on information in one part of the map can therefore improve another part of the map. So it's kind of magical in a sense, but it's very simple in another sense. It's just because one Fourier term affects everything, an error in one term leads to correlated errors. So fixing a Fourier term based on one place in the map can improve another place. So let's do that. So we're going to try to find Fourier terms that improve the map in one place so that we can improve it everywhere. So here's the approach. And we're going to call this map phasing. It's map phasing because we're generating phases, actually, and amplitudes based on our expectations of what a map ought to look like. So here's what we're going to do. We have a map. We're going to back calculate to get Fourier coefficients for the map. Then we're going to, one Fourier term at a time, we're going to take the Fourier term out. So we can calculate a map without that Fourier term, and it'll look a little worse. And then we'll ask, what version of that Fourier term can we add back in that makes the best looking map everywhere? And we're going to judge it by, for example, a flatter solvent, or better histograms, or anything else that we can feed in there. For example, if there was symmetry in the map that was not used in reconstruction, we can ask, does the new map show better symmetry? If so, that value of that Fourier term is probably a better one. Or we could say, I have a model or a value of density that I think is probably relatively accurate in this part of the map. Does this Fourier term lead to density that looks like what I think it ought to look like? We'll talk about that one if we have time later, and why in this procedure that doesn't bias things too severely. Okay, back to the simple version, solvent and histograms. So our new Fourier terms, so we took them, generated Fourier terms one at a time. We have a new list of Fourier terms. we can call that the coefficients of a map, and we can calculate that map, and that is a map phasing map, and that will often be better than the original. It's a little tricky, but in fact, that new map is also, under optimal circumstances, independent of the original in that the errors are new errors. Okay, so what's the whole procedure then for density modification? We're going to start with two half maps, is the same two that I showed you. First, we're going to identify where the solvent and protein are and generate histograms. So we're going to average the maps and sharpen them to create a full map. We'll identify the macromolecule and solvent regions. Macromolecule is going to be where there's a lot of variability in the density. The solvent is where it's relatively flat. We're going to use the density histograms in the macromolecule and solvent regions to generate histograms for the macromolecule and solvent. We don't have to use those histograms. We can use any of a variety of histograms for targets. And sometimes these are the best ones. Sometimes the best ones are histograms from model proteins, same as we use in crystallography, for example. So now we have half maps and targets of what we think the density ought to have the characteristics of the density. If we had symmetry, we would also at this point generate density from one symmetry mate and map it to the other one. So second step is going to be done in Fourier space. That first part was all in real space. So in Fourier space, we're going to take these two maps, calculate Fourier terms that represent the same thing. So we have two sets of Fourier coefficients. For each one of these, we're going to ask, just as in the previous slide, take out one Fourier coefficient, ask what value of that Fourier coefficient leads to a map that generates histograms that are as close as possible to the target. And similarly, if there's symmetry, include that. This generates map phasing estimates of the Fourier terms, and there's one set for each half map. So now we have 4 maps. And we're going to then calculate the weighted average of the 2 original and 2 map phasing sets of Fourier terms, and that generates our density modified map. Okay, any questions on this step? I'll give you a second to think. If you have a question, I'd be happy to answer on this one. We're going to move on and actually do it now in a second.
Hi, Tom. One quick question. So the combination, is this with both the amplitudes and the phases, or just with the phases as in crystallography?
This is amplitudes and phases. So it's averaging vectors in reciprocal space. Yes.
Okay, great. Thank you.
And the averaging can take into account a lot of different things. For example, you can try to estimate the errors in each map and then weight based on the errors in the map, and that's the standard way to do it. You can also try to estimate errors locally in each map, and then so you might have a different weighting for different parts of different maps. That can help in some cases as well. Okay, so let's do it. So we're gonna go, this is a picture of the Phenix GUI here with all of my projects on the left side and things to do on the right side. And we're gonna get some data from the tutorials that Phenix is supplied with. So if you download a nightly build now or next week when we have a new full official version of Phenix, if you download that, it will contain already the data that's necessary to do this tutorial that we're basically running right now. So I'm not going to do it in real time. I'm going to show you pictures of some of the things. So to generate tutorial data, you hit new project, that pops up a little GUI, and then you say set up tutorial data. And then that sets up a list that you can choose from, and we're going to choose the human apoferritin density modification, model building, and refinement at 1.8 angstroms. So if we do that, that'll generate a new project and it'll have a little check mark next to it, like the one here on the left. So now that generated a little directory with data in it, ready for us to do something. So what we want to do here is we're going to do density, we're finding the half maps, we're going to do density modification on them. So that's going to be under the cryo-EM tab. And in the cryo-EM tab, there's a button that says Resolve cryo-EM. So we hit that, and that puts up a little window, which we then fill in with the things that I've shown here. And the kind of things that we want to put in are a title, which I already did there, and then 2 half maps. And these, let me just mention the characteristics of these half maps. These half maps should be as unprocessed as possible. So one of the things I kind of glossed over in the version of telling you how this works is that errors in the maps do have to be errors in the Fourier coefficients of those maps, and the errors can't be local errors. And what that means is that if a map has already been processed, let's say masked, so that outside the protein region, the values of all the density is all 0, let's say. That map has been very processed, and the Fourier coefficients for that map don't have independent errors in the different Fourier coefficients. The errors in the Fourier coefficients for that masked map are highly correlated between Fourier coefficients so as to make the outside region flat and the region in the protein not flat. So those map coefficients don't satisfy the conditions necessary to do density modification usefully. Now, all cryo-EM maps are masked at some level, but I'm just saying that the less of that has been done, the better it's going to work. Another way to think about that is the noisier the solvent is, the more improvement you're going to see. There's a balance there because in your density, in your data processing, of course, the better data processing you do, the flatter the solvent will get. Bottom line is generally get the best map you can to start off with, using as little processing as possible that's specific to local regions, such as flattening the solvent or doing processing that changes the resolution in local places of the map, and then use that map for this, those half maps. Okay. You set the resolution. You don't have to, it can be done by default. If you do it by default, it will calculate a Fourier shell correlation, find the place where that goes to 0.143 and use that as the resolution. Resolution for density modification, you can also set if you want. That will also be done for you by default if you don't put something in. These are parameters that it is useful to change and find which ones work best for you in this particular case. There's no general rule about exactly what's the best. A sequence file. Why do I need a sequence file? Actually, the sequence file is not for the sequence at this point. It's to tell the program how much stuff there is in your box of density so that it knows how big a region approximately is your macromolecule is going to occupy. You can also specify that with molecular mass or solvent content. You might want to say how many processors you want to use. The more you have, the quicker it goes. And another thing that in this particular tutorial helps, and sometimes this helps for high resolution data, you can density modify maps that are quote unquote unsharpened. During the density modification process, in the very first step, I mentioned that the half maps are sharpened and averaged to create a starting map. Those are sharpened by using half map sharpening. Basically, the resolution dependence depends on the Fourier shell correlation between those half maps. Usually that's the right thing to do, but in some cases, better density modification occurs if you don't do that and you just apply an overall B factor. So this particular case, that turns out to be true. This is another thing that you may vary if things don't work just the way you want them. Then we're ready to go. We just hit run. This tutorial takes about 15 minutes to run, and it requires quite a bit of memory. If you don't have at least 8 gigabytes of memory on your computer, you wouldn't want to run this tutorial. In particular, you wouldn't want to use 4 processors unless you had that much. If you had less memory, try it with fewer processors and maybe it won't crash. So a lot of the cryo-EM tools that we have with big maps use a lot of memory. Okay, so we ran that, now it's 15 minutes later. And we got a results tab. And what do we want to look at? Well, one of the things we want to look at is just what's the estimated resolution improvement from density modification. This case, it's pretty small, 0.05 angstroms. And since it starts from pretty high resolution, that's kind of okay. And the value you get for this will depend on the characteristics of your map. The kind of things that will make a big difference are what's the starting resolution of the map. Lower resolution often improves more. How bad the map is overall as a function of resolution will have a big effect. If your map is very good all the way up to a high resolution, suddenly gets much worse, you'll get a very small density modification improvement, as in this case. If your map is relatively poor throughout, then you might get a much bigger improvement overall in resolution. So next thing we can look at is the Fourier shell correlation of the starting half maps. And in the lower right corner, it shows that this map falls off at a resolution of about 1.8 angstroms to a Fourier shell correlation. That is a correlation in this shell of resolution between the Fourier coefficients of the 2 half maps of 0.143, which corresponds to an estimated Fourier shell correlation between the average of the half maps and the true map, which we don't know, of about 0.5. Notice in this picture that up to a resolution of maybe 2.3 angstroms or so, the 2 half maps have an agreement of 0.9 or better. So that says at all but the highest resolution, these 2 half maps are already essentially identical. And aside from errors that are systematic, they're both basically perfect. So you don't expect improvement in the low resolution terms. You expect improvement only in the high resolution, which is what we find. So now we're going to look at the Fourier shell correlation estimated based on the statistics of the density modification between the original and the true and the density modified in the true. So this shows that. So the brown is the original map, which falls off to a 0.5 estimated correlation to the true map at about 1.8 angstroms. And the blue is the density modified map, which is a little bit finer resolution. And you can notice that at any particular resolution, the estimated quality of the density modified map is quite a bit better in this range of resolution. At lower resolution, they're essentially identical because it's already very good. So what do we see when we look at these maps? So the left-hand picture here is the average of the half maps, and I've sharpened these in a very special way. I've tried to make the map on the left have the same resolution dependence, the same power as a function of resolution as the map on the right. So the map on the right is our density modified map. The map on the left is our average of half maps, and I've resolution matched them to the density modified map. You can do this with the Phenix tool auto sharpen using external sharpening as the keyword. So you feed in your map, you feed in this case, it's average map, and you feed in your other map to target, the density modified map, and you tell it to match your map, resolution dependence, to this one. This gives a map where the resolution dependence is matched, and therefore the differences that we see are differences due to intrinsic differences in the map, not just its overall resolution dependence. This is a really problematic thing in comparing two cryo-EM maps. You give me 2 maps and you just sharpen one of them, I might say it's better. But this will tell you whether it really is better looking at it this way. It's not perfect either, but it's the best way I know how to do it. And then the second part of this is we've set the contour level on the map on the left and the map on the right such that they enclose equal volumes. That way, I didn't set the contour level to make it look good. I set the contour levels to make them equal. Actually, what I really did is I did set the one on the right to look good, and I set the left one to match the one on the right. So if you look at them, yes, the density modified map looks better. You can see some things such as this phenylalanine that you barely see in the other map, and here's another one you don't see it all in the other map. But many of the features are very similar in the two maps. And this is typical. The low resolution features, or even most high resolution features, are very similar, but you get more high resolution information at the very highest resolution values. Okay, so let's see. Any quick questions so far on that either?
So I have a few questions here from the chat. I think you touched on it earlier, but I think general theme of the questions is, before you do the density modification, where do you want your maps to be as you come into this process? Like, do you want, how do you,
Yes.
What's your sort of masking? Do you want fine maps, composite maps? Like, are we targeting flatter solvents? So you should leave in sort of solvent regions, or just best practices for going into the density modification.
These are great questions and very important. So basic answer is going to be as unprocessed as possible, but still the best looking maps that you can have that are as unprocessed as possible. Second thing is, if there's some aspect of this map that is problematic, like your map has this huge peak of density in it that has nothing to do with anything that you think is a total artifact, it would be beneficial to mask the map to avoid that density. You can do that by supplying a mask in the first step of density modification. I'll just show you that, go back to that real quick. So there's a place where you can put in a mask file. So the reason to put in a mask file is because you want to tell the program specifically what to avoid. Generally speaking, you don't want to do that because you want to keep everything in there. But if you know something about the map that the program can't know, that's a great thing to put in there. Second, yes, you can box the map beforehand if you wish, and that's sort of equivalent to supplying a mask file in a way, not exactly the same, but very similar. So if you box the map, box it such that you include your entire molecule and a bit of solvent around it, such that your solvent content effectively is about 75%. That's what the program actually does itself. The first step involves boxing the map so as to get rid of the huge volume of pretty much nothing in most cryo-EM maps that extends a long ways. So, and the reason the program actually does that is a technical one. It's a deficiency in the procedure. The procedure assumes that the solvent has fairly uniform noise levels. But in a typical cryo-EM map, the solvent noise is very high near the molecule and very low far away. So by boxing it to make a smaller region, the uniformity of the solvent noise is more constant. So you can do that yourself if you want. And if you supply a boxed map, then you specify down here in the lower corner, I'm showing you the thing that says box before analysis. If it's already been boxed, then you do not check this box. If you supply a full map that has not been boxed, you check this box and say, yes, box it before analysis. I haven't done studies that are systematic about focused maps versus not focused maps. I would just give that, you could give it a try on a focused map and only look at the focused map part. It could be tricky because the program is assuming that the whole macromolecule region is somewhat constant in its density values, but if it's a focused map, that may be very untrue. So if you try that, let me know how it goes. I don't know what's going to be best with that. Any more questions on what input maps? Great. Okay. So, all right, we got time. So now let's build a model into this map. I'm not going to show you all the details of that. I'm going to show you the high level version of it. And I'm going to focus on the steps to fix the problems, actually, rather than the steps to build the model. So we have our density modified map on the right. And we have a sequence file. And we have information that our map has some symmetry. So this particular map, human apoferritin, is octahedral symmetry, has 24 identical subunits. And so we have a little tool to find that symmetry so that when in the model building process, you don't have to build 24 of them, you only have to build one. So let's do that first. So we're going to go to map symmetry tool, and we're going to use that to find the symmetry. Basically, we're just going to put in the map. We're going to put in that we want to find the symmetry, and it'll find it for us. This works great if the symmetry is something simple. It's any popular symmetry, and if the symmetry elements are along cell axes, this works terrific. If you have symmetry that's not along cell axes, then you can also find it with map symmetry, but it doesn't always work, and it takes a really long time. The simple way to do it is you just spin the map along map symmetry axis, along map axes, find whether there's symmetry, and it's really easy. If you don't have that, then you have to take a little sphere of density, try to find it in other parts of the map, find the relationships amongst all those, and then put it all together to get your symmetry. So that's harder, doesn't always work. So, but in most cases, you just find the map symmetry. So then we're going to go to map to model. That's our cryo-EM model building tool, and we'll use all defaults, put in resolution of 2, put in the symmetry we just found so it doesn't have to look for everything, and we put in our density modified map, and we hit go. And then put in how many processors we have, and once again, more the better. And this takes about a half hour on my computer to run, and then this is what we get. So these are 2 snapshots of parts of this human apoferritin. And what you notice in these snapshots are, so let's look at the one on the right here. Part of the map is built, the model looks great. It fits the map extremely well. And you can see all the hydroxyls, and you can see our tryptophan. It looks terrific. And so most of the model looks like that. But some of the parts don't. So we can look up on the right here. Here's a place where it's clearly mistraced. So clearly the density should go around. The model should go over here. Didn't do that. And on the left, similarly, the left-hand part looks pretty good, but it got mistraced in here. And actually on the left, it isn't completely good. You notice that there's this long side chain, which is going to be an arginine later. It didn't find that side chain. So we have a few things to fix. And in this particular case, it's pretty easy because it's a high resolution map. Most of it fits very well. And all we have to do in this particular case is identify what parts were bad. So in this case, we could just look at this one and say residues 6 to 9 are bad here, clearly. And we can look at this one, residues 154 to 162 are bad. And so what do we do with that information? Well, since most of it's pretty good, what we're going to do is we're going to cut out the bad parts, and then we're going to reassign sequence to model in the parts that were good. We're going to refine in here, but I'm not going to show that. And then after we reassign the sequence, we're going to know what residue is at the beginning and end of each of these gaps. So we'll know in this case that it's 6 to 9. So I say 6 to 9 here, but actually that isn't the residue numbers that are there. So we will know it's 6 to 9. And then we know that we have to fill in 7 and 8. And here we know it's 154 to 162. So we have to fill in 155 to 161. So we know exactly what to do. Fitting loops that way is a lot easier than fitting loops where you don't know what's connected or you don't know how many residues go in there. So let's just do those things pretty quickly. So first we're going to cut out a piece, and that's with map box. Oops, sorry, one step before. We're going to make this all easier and quicker by cutting out a piece of the map that's just the size of one chain of our protein. So we're going to step back. We're just going to figure out, we're going to make a small map and a small model, so everything is going to go quickly. So you don't have to do this, but it's very convenient. So we're going to use Mapbox, feed in the density modified map and the single chain model that we built with that's got some problems. We're going to run Mapbox, and now we have a small map and a small model. Okay. Second, we're going to run this tool here called sequence from map. And that sequence from map is going to identify for us that new sequence register and fill in gaps. So let's do that. Mapbox. And here's the sequence from map tool. Oh, sorry. And we're going to cut out the piece. So PDB tools, we're going to cut out residues 6 to 9 with PDB tools. And then sequence from map. And the entries, the inputs for sequence from map are going to be the map file. In this case, it's going to be the small map file, the model, just a single chain, and the sequence. And this model is going to be the model where we took out residues 6 to 9. So we removed the gap, removed the residues in the bad residues. We put in the gapped model. We put in this into sequence from map, and we check the little box, here's the key, sequence and fit loops. So that says, redo the assignment of the sequence of the pieces we put in and fit the loops that result. So how does it redo that sequence? It takes each fragment. So we have a model that goes, in this case, from 1 to 6, for example, and then it compares the model sidechain positions, the sidechain positions that would be present from this, identified from the model, to what density is actually there, compares that to a library of shapes of sidechains that are derived from cryo-EM structures, and then identifies the most likely sidechains at each place, and does a probabilistic fit of the sequence to that region. It does it for all of them, and it has several possibilities for where each particular part of the model fits into the sequence, puts all those together to find the best overall fit, and then builds in the side chains according to that best fit. Then we have a gapped model that has the sequence assigned. Then we use fit loops to fill in those gaps, and that's also done automatically. Okay, so then the result of that is, so here are the maps and model I showed you before, and then after fitting, and after cutting out and fitting, it pops it right in. So you can see that on the right-hand side, for example, it's fit this loop much more nicely, put in this proline where it belongs. On the left-hand side, now we have that arginine fit where there was no side chain before, and the main chain is now built in correctly. So overall, for this high resolution structure with very good density, it's very easy to fix. For a lower resolution structure, you're going to have to do more work, but this kind of procedure is a great way to start out. The more model that you've built correctly to start off with, the more likely you are to be able to succeed with this method. If this doesn't work, then you might build things yourself in Coop, for example, or some other tool, and then you can feed those into the automatic rebuilding process as well. Okay, so overall, here's some things, continuing the discussion we had earlier from your questions, what kind of things we want to try and what to keep in mind. So yes, if you're doing cryo-EM and you have half maps, which you normally will, try density modification. It won't always work, in the sense that it won't always make a map that's more useful than you start off with. But a lot of the time it will, and sometimes it's a lot better, sometimes it's just a little better. But give it a try, it doesn't take very long, and it's easy to do. and look for improvements on the order of 0.1 or 0.05 to 0.3 angstroms. Those are kind of the normal range of what to expect. And the improvement value that the program provides to you, that's the best estimate we can give you, but it isn't that accurate, I would say. So if a number is very big, usually that means it worked well, but it doesn't prove it. And if it's small, usually didn't do that much, but it doesn't prove it either. So I wouldn't put too much stock in the exact numbers about estimated improvement in resolution. And also be aware that in the cryo-EM field, if that's not your field, resolution is a huge debate. And so it's best to avoid any discussion at all about what is the exact resolution of my map and did I improve it? It's better to focus on, I can see this thing that I couldn't see before. That's what's important anyways. It works best with half maps that have uniform noise. And model building, I didn't really talk a lot about it, but the map to model will build for you protein, RNA, or DNA. Builds protein best. The others are not as good, but it'll try. You can do all of them at the same time. It's actually done one at a time, and then whichever fits a piece of the map better, that's the one that's kept. But you can do it for anything, including a ribosome. Takes a long time, and best on multiprocessor or SunGrid engine machines or something like that with lots of processors. Really helps if you have something that's very big. Another thing to think about is I showed you about boxing a little piece of a map. It's also very helpful in model building. So it's good to break your map down into little pieces and do your model building on the pieces individually. That gives you more control. So you can make a box around a point that you specify. You can make a box around a dummy set of atoms that you create. If you want to make a box, for example, that has a certain dimension, you can make a little PDB file that has a water in one corner and a water in the far other corner, and then that defines a box. And then you can do Phenix map box with that pseudo model in your map, and it will cut that piece out. Mapbox can also just take grid coordinates and you can tell it what to box out. So you can have a lot of control about that. But my point is, make little pieces of your map, build into those, and then you can put them all together later. And fixing your model by cutting out misfit segments and rebuilding with sequence from map using that sequence and fit loops tool keyword is very, very helpful. And this tutorial, the walkthrough, and the scripts are all supplied with the latest version of Phenix. So there's a tutorial that describes everything I just went through, for example, and the data's all there. And so you can do that at home and take you an hour to do everything that I just showed you. There's also a script that you can just run and it'll just do it all for you. Okay, and once again, thanks to SBGrid for doing this. This talk's on the web, and thanks to all the Phenix developers. This is a real team effort here, and I'm the beneficiary of all the work from all the other Phenix developers. And once again, thank all of you, and everybody stay safe. Any questions?
If you have questions and you're mic'd, you can raise your hand and I will call on people. I've got a few here from the chat that I'll pass on first. So sort of lumping these into general categories. I think one general category is just based on the sample and the model. Like if you're working on a large virus, say, and you've already imposed symmetry, you've got an asymmetric unit. Is that a reasonable place to start with density modification? Should you back up?
Yes. So suppose you have something like a virus that has huge amount of symmetry. The density modification must be on the whole thing. It won't work if you just cut out a little teeny piece. So if you cut out a little teeny piece, what you'll end up with is the same thing that you would get if you did real space manipulations like histogram matching. That'd be the best possible result if you cut out a little piece. And the reason is that the information about what to fix is on the scale of the whole map, in particular in the solvent region. So if you just cut out a little teeny piece, the Fourier coefficients that you create by doing that have all kinds of correlations amongst themselves that don't have anything to do with the information you're trying to get. If you have the whole map, if you're very lucky, then the Fourier coefficients have errors that are independent between different Fourier coefficients. It's not exactly true. I just to make sure that everybody realizes that there's a technical thing that makes that not quite so, and that is that your object is very small compared to the box. Therefore, all Fourier coefficients are highly correlated, but only in a special way. So Fourier coefficients that are close have indices that are very similar to each other because the box is big and the molecule is small. Fourier coefficients that have similar indices have very similar values. That's not what I'm talking about. I'm talking about if you make a little teeny box and you cut it out, the Fourier coefficients there have all kinds of correlations that say outside this box everything is zero. Okay, so that's a different situation. So bottom line is density modification requires the whole molecule and something around it, and optimally the whole box. So you don't use a little piece. And then, so you do the density modification on the whole thing just as is. The symmetry actually doesn't matter at this stage. The symmetry will be maintained by the density modification procedure. So if the molecule comes in symmetric, basically it goes out symmetric. That's not quite the right statement. If the density in the map is exactly symmetric coming in within numerical error, it will go out exactly symmetric as well. Now, once you've done your density modification, then it would be a fine idea to cut out just a little piece that contains the asymmetric part of your virus and work with that so you don't have to work with everything. It'll speed everything up. At the end of whatever you're doing, you can regenerate the whole molecule using the symmetry that you identified. You can identify that symmetry with the map symmetry tool, or you can identify it from your PDB file as well, either way. So basically, if you have one asymmetric unit worth of a PDB of a model and a symmetry, you can use apply symmetry, Phenix apply symmetry to make the whole molecule. Once you're all done with that, you will want to refine the entire molecule with symmetry, with the whole map. The density modified map is fine there at the end, so as to refine including any contacts between symmetry related molecules. So if you cut out a little piece, then you might get a side chain in a bad position such that if you put it back with the other ones, it wouldn't fit. So you need to put them all back together at the very end, refine the whole thing, make sure there aren't any bad contacts, do your validation, check things, fix things, and then you're done. And you'll hear more about that from Pavel and Dorothy later.
So sort of related question is things like nanodiscs or big do you have any recommendations around special sample types, or is this kind of a general nanodiscs work, viruses work?
Yeah, actually, I would say more the simpler the system, the more likely it is to work. Nanodiscs are a little bit problematic in that they have different components in different places, and the densities in those different components are not uniform. And so the program as it's set up is expecting to see some place where all the action is, like a protein, and then some place where there's no action, more or less, that's the solvent. If there's three categories, like lipid, protein, solvent, it doesn't work as well. And you may have to fool around a little bit with perhaps supplying a mask to say that everything inside this lipid plus protein, let's count that as our molecule. So that's a little bit of experimentation required, and we don't have a great solution at the moment for that. So give it a try, but it may be not as good in cases where there's multiple types of components that have different scattering properties.
Yeah, so we had a related, if you have a component that is, it's present, but it's not resolved, say like a DNA complex or something, and you can see some of the DNA, but not all of the DNA. you could take a shot at sort of masking out the general area that you think it might be in, or you just kind of like let it ride? And
So that one, I would sort of do the opposite of use a mask again, but I do it the opposite way as for the nanodisk one. For the DNA one where you think it's there and you can sort of see it a little bit, the goal here then is to make sure the program thinks that it is protein or that it is macromolecule. So here a mask is useful to say to tell the program, keep all of this. So you can make a mask that includes the whole molecule, including the DNA that's very poorly resolved, and just apply that as a mask. And it will use it instead of trying to generate its own, which might mask out that DNA.
one other question, similarly, ligands. Would it be reasonable to expect ligand density to improve after density modification?
Yeah, I don't have a lot of experience with ligands. I would expect ligand density to improve in the same way that the protein density improves. But I haven't looked at ligand density specifically in relatively high resolution maps to see exactly how it behaves. So I'd be happy to hear feedback from others on how that works, but I don't see any particular reason it shouldn't work. One thing to note is, so density modification, not including a model, should improve the whole region where the molecule is present. If there's a ligand, and the ligand is very weak, of course, then it might be masked out automatically in the same way as the DNA that we were just talking about. So in that case, if that seems to happen, then you could supply a mask that includes the ligand just in the same way as the DNA, which is telling it, let's keep this in the process, don't mask it out. Don't try to flatten this and call it solvent. So that's if you have, or just doing density modification with no model. I didn't talk a lot about density modification with a model, but you can do that. If you supply a model, the procedure that will happen is that the model will be randomized by default, make 8 models for each half map, refine them all separately, create an ensemble for each half map, use the variability amongst the models in each half map as an estimate of error in that model-based density. You include that model-based density in the density modification process as a target, and that can improve the map. Turns out that doesn't have a huge amount of model bias because of the multi-model procedure and because of the way the density is used as a target, not as this is the density. That can improve the map. I have not yet seen that improve something like ligand density. It's possible it could, but so it's worth a try, but I haven't actually seen that help yet.
One group of questions is sort of centered around when sharpening is appropriate. Is it appropriate to do sharpening after the density modification?
Yeah, this is a very good question. So the density modification procedure essentially produces a map that is sharpened, and based on the statistics calculated during density modification, it is already optimally sharpened. It's not necessarily perfect, however, so it's perfectly fine, if you wish, after density modification, to apply some sharpening procedure. So the sharpening procedures you might apply would be, number one, if you have a good model-based sharpening with Phenix Auto Sharpen, basically matches the resolution dependence of the map. It adjusts the resolution dependence of the map based on the correlation in the Fourier shell correlation between the map and the model. So resolution shells where the map and the model agree well, those are accentuated in the sharpened map, and those where they agree poorly are weakened in that map. Though that map can sometimes be a better map for looking at than the original density modified map. So if you have a good model, that's definitely something to do. If you run density modification with models, that's actually the procedure that's carried out. It generates a new density modified map, including the model information. At the very end, it takes the best model that it can create and uses that to auto sharpen the final map, and that's what it produces for you. So yes, auto sharpening using a model is a fine thing. You can also auto sharpen using the density modified half maps as information about how to sharpen it. So basically you run auto sharpen with your density modified map as the main map, 2 half maps that are your density modified half maps. A third version is exactly the same thing, but you can use the original maps, half maps. You would think that wouldn't work so well, but actually it's not so bad either. You can also auto sharpen with no model information and no other outside map information, just using the standard auto sharpening procedure that maximizes surface area. I wouldn't necessarily recommend that. It's okay to try it. And if it works and gives you a good map, fine. But I wouldn't expect it to work that well because the solvent has been flattened so that the surface area method would not be expected to work so well.
Any guidelines around resolution and when you'd expect this to be most effective, or is it a sort of the better the resolution, the better off you'll be?
Well, actually, it's a little counterintuitive. A lot of times, the worse resolution, you get better result, a more dramatic result. So I've seen a couple of cases that are really dramatic, and those are all in the low resolution range, in the 4 to 6 angstrom resolution range, where it's like this map is like really bad, and then you run this, and they're like, wow, that's totally different map. That happens in the low resolution range. In the high resolution range, typically it sharpens up, it looks a little bit better, and things are a little bit cleaner. I haven't seen anything where like this is a totally different map from a high resolution map, because the high resolution maps typically are actually very good up to high resolution.
Yeah, makes sense. So had a sort of technical question about constructing molecular envelopes. So how do you construct a molecular envelope from variance? Use a threshold or something more rigorous?
Yeah, so the way the molecular envelope is calculated, it's actually the same trick we use in our crystallographic tool. It's actually the same tool exactly as Resolve that does this. Basically, you go through the entire map, and at each point in the map, you draw a sphere. You make a sphere that's a certain radius, and that radius is going to affect the result. And typically, that radius is about the same as the resolution, more or less. And then you calculate the variance within that sphere, and then that's a value at that particular point. So now you have a variance map for the whole map, where the number is big where the protein is, and it's small where the solvent is. And then we have some idea about what fraction total ought to be protein and solvent. And then we turn that variance map into a z-score. Z-score just means value at this place minus the mean of the whole map divided by the variance of the whole, divided by the standard deviation of the whole map. So now we have a z-map. It basically says how different this point is from a typical point in the map. And then we use that as a probabilistic estimate of whether this particular point is in the protein or solvent, and we apply Bayes' rule to that thing and generate an estimate of probability for. So Bayes' rule is including the solvent fraction, and that's going to give us an estimate of the probability that this point is in the protein region, and that is used to generate the map. A mask with a threshold of 50-50 is typically used on that one, and in some stages of density modification, the whole probability is used. In some stages, a mask is generated from that probabilistic map.
All right, so we're coming up on our hour. We've got one more question from Zhongli. Just a practical question. You showed how to do a single chain in the automated building. Like if you've got multiple subunits, how would you proceed?
Yeah, the procedure is exactly the same. You supply a sequence file that has multiple chains in it, and it can just be any FASTA file or something like that, or you can just put in a sequence of letters, separate them by a blank line for different chains, and let it run, and it will try to assign what sequence goes with what part of the model. Basically, if you have a low resolution model, lower than, let's say, 3.5 angstroms, it's not going to be able to figure out this is subunit A, this is subunit B. It won't do that well. It'll build a bunch of stuff and it won't know for sure what most of it is. If you have high resolution, better than 3, a lot of it will be assigned correctly to sequence and therefore correctly assigned to what domain is what.
Great. Well, with that, Tom, thank you very much. I would urge people to take advantage of the tutorials that are in Phenix because they're fantastic. There's this tutorial, but there's tutorials for all major workflows in Phenix. They have data. It's all there. You can work through it. It's all online. You've got guides. If you're a software developer, consider packaging your tool with some test data so that users can learn how to use it on good data. And it's really quite nice. And with that, happy model building. And go ahead, Pete.
One quick question about the demos. When you mentioned the amount of RAM for running this demo, was that
Yes.
80 gigs or 8 gigs?
8.
Okay. 80 would have been a lot harder. Thank you.
Yeah, no, 8. Yeah, it's my MacBook Air has 8, and that's what I'm using.
Thanks.
All right. Great. Thank you very much.
Okay, bye everybody.
Bye.